So welcome everyone to the second, Alumni MasterClass. Today, the MasterClass will be taken by Dr. Aishwarya Agrawal. She is a BTech graduate of IIT Gandhinagar. She graduated in 2014 in electrical engineering. After graduating from IIT Gandhinagar, she pursued her Ph.D. from Georgia Tech. And then Dr. Agrawal is currently working as a research scientist at DeepMind in their London office. She will also be joining very recently with University of Montreal and Mila as an assistant professor in fall 2020, which is a very exciting news. She has won several awards, and you would also see that she has declined some of the fellowships that she has received. So she has been she has received NVIDIA graduate fellowship in 2018 and 2019. She has been selected as one of the rising stars in EECS 2018. And she's a very accomplished alum of IIT Gandhinagar, and she has been my student. Welcome, Aishwarya, and thank you very much for agreeing to give this masterclass. I welcome all the students, alumni, and faculty members of IIT Gandhinagar to this talk. So before we start, few things. Aishwarya would like to take questions during the talk. If you have questions, please type the questions in the chat. Aishwarya, over to you. Thank you so much for joining. She's joining us today from London. Welcome, Aishwarya. Over to you.
All right. Thank you so much for that wonderful introduction. So, hi everyone. First of all, I would like to thank Professor Jason Manjali for inviting me to give a talk. I'm very excited to be speaking today. Usually I give talks about visual question answering, which is my area of expertise. But in this talk, I have tried to provide a broader view of AI. And of course, I'll still be talking about visual question answering. You can't escape that. And at the same time, I've also tried to interlace elements from my personal life in an attempt to provide a more transparent view of my journey with AI. So with that, let's get started, and feel free to stop me in between to ask questions. I want this to be useful for you, so I want this to be as interactive as possible. So do ask questions. Whenever something is not clear, please stop me and ask before I go ahead. All right. So, 7 years ago, I was a third-year undergraduate at IIT Gandhinagar, just like most of you guys. I was in electrical engineering, and although I was pursuing a minor in computer science and engineering, I wasn't too fond of programming. But I was keen to learn image processing. And now you might be thinking that image processing also involves programming, so how come? You're right, but for me that was still fine, because you could program in MATLAB, which was something I was comfortable with at that point, and I was more excited about the end result, the processed image, rather than the process of programming itself. Anyways, around the same time, I came across an opportunity to pursue a summer internship at University of Washington on image processing, and I applied for it and got selected. So what's the point of telling you all this? Well, the point is that this was the beginning of my journey of AI. That internship developed my interest in image processing and computer vision. And it sort of prepared me mentally to pursue a graduate degree in the area of computer vision, because I was curious to learn more about this area. So I came back from the internship and did the expected. I pursued a BTech project related to computer vision in the area of computational photography. so that my CV, when I apply to graduate school, has at least a couple of projects in the area. I then applied to 10 to 12 different schools and got admitted to Virginia Tech. And those of you who noticed in the introduction, it was mentioned that I was at Georgia Tech, and that was because after 3 years of my PhD at Virginia Tech, my advisors moved to Georgia Tech, and they were nice enough to take their students with them. So I finished at Georgia Tech. All right, so when I was applying to graduate school, my profile as an undergraduate wanting to pursue a graduate degree in computer vision wasn't that great. I had not even taken a course in machine learning, which was the workhorse of computer vision at that time. And no wonder I got rejected from most of the top schools. But I got lucky. My BTP advisor, Professor Shanmuganathan Raman, I think who is in the call, he had a knack for identifying potentially good PhD advisors from not so well-known universities. He knew the field. He was the one who advised me to apply to Virginia Tech because he knew about Devi, Parikh and Dhruv, Batra, who I ended up pursuing my PhD with. So, this is how I started my journey of AI, not knowing much about the area and not even knowing who to pursue PhD with. And I was lucky to have Professor Raman to guide me in the right direction. So with that, I started my grad school at Virginia Tech, advised by Dhruv, Batra, and closely collaborating with Devi, Parikh. And there I started learning about machine learning, which is very important if you want to do computer vision. Think of machine learning as the tool to be able to do computer vision, just like math is a tool to be able to do engineering. And I also learned about computer vision in more detail. So now let's see what computer vision and machine learning are. And before we move forward, this is the outline of my talk. I already talked about the beginning of how this journey of AI started. And now let's go into the basics, computer vision and machine learning. And I'll try to give you a flavor of how I learned it. All right. So what is computer vision, right? At a high level, computer vision refers to the science of making computers see. So now the question is, what does it mean for a computer to see? Imagine that you are visiting this amusement park, which is shown in this picture, right? It is very easy for you as a human to identify various aspects of the scene. For instance, you can recognize that this is a sky, this is water, there is a tree here, there is another tree, there are more trees, those are some pedestrians, that is a Ferris wheel, that is a ride, those are some more rides, that writing says 12E, that writing says max air, there are people waiting in the line, there are people sitting on the right, this is an amusement park, and so on. So as a human, we can identify the objects, the activities, scenes, writing, gesture, and many more things by looking at this picture, right? So what we do in computer vision is to try and program computers to be able to automatically identify all these things. Does that make sense? If I don't hear any ping, I will assume all is good. Okay, so in computer vision, the input to the computer is an image, for example, this image that you saw. And in the output, we expect it to name all the things that we as humans can name, like sky, water, trees, and so on. So what is the challenge in programming a computer to do this? Well, let me show you this picture. What do you think is shown in this pixelated image? And I really want you to think about it and provide me an answer, and I'm going to wait for your answer. And Professor Jason, can you unmute and let me know what students wrote? I can't see the Zoom chat window.
Abraham Lincoln.
And how many people said that?
At least 3 of them. Now the 4th, yeah.
Awesome. You guys are great. Okay, so yeah, as you can identify at the very least that this is a picture of a person. And as most, sorry, you said something?
So Srihari, you want to ask some questions. Srihari, you would like to ask? Srihari, can you hear me?
So sorry, this problem.
Yeah, go on. I think Aishwarya, I think you should continue.
Okay,
please.
all right. So as I was saying that you can identify that this pixelated image is an image of a person, and you can in fact even identify that this is a picture of Abraham Lincoln, as most of you did. And notice that you could do this only from 12 by 16 image. It's just like 192 pixels, not even 200 pixels. Isn't that amazing? Now let's see how a computer sees this image. So if you present this image to a computer, for it, this image is essentially a matrix consisting of a bunch of numbers. So at high level, each cell in this matrix corresponds to a pixel value of that image, and that basically encodes the intensity of the light present in that region of the image. And this is like very hand-wavy way of explaining it. Okay, so now we expect the computer to be able to identify that this is a picture of a person from this matrix of numbers, right? But we as humans can do it. Let's see again. So how did you identify this as a person? You probably were able to identify this image as a person because you saw a pattern which is depicting something familiar to you. So for example, you could identify that this region represents the face of an image, this region represents the neck area of the person, and this is the shoulder area of the person, right? So as humans, we are pretty good at identifying patterns. But imagine what it would take for a computer to do the same job of identifying patterns from these arrangement of numbers in the matrix. Well, so one way to think about solving this task for a computer is to write a program. So, you know, like those of you who are pursuing computer science, like how you write a program to sort a list of numbers, right? One might think, well, can't I write a program for the computer to identify this pattern and recognize this image as a person? So in this case, if you were to write a program, you have the data, which is the image. You have a program that you just wrote. You can feed that to a computer, and you should be able to get the output, which is a label saying that this image is a person's image, right? So what's the challenge? Turns out it is too difficult to write that program that codifies what pattern represents a person. Why? Because it is difficult to know the exact pattern. Plus, the program that you write for identifying one person may not hold for another person because there is just so much variation across patterns for different people. And just to give you a sense for how hard it is to write this program, in 1966, Marvin Minsky, who was a well-known AI scientist, he asked an undergraduate student, just like you guys, to link a camera to a computer and get the computer to describe what it saw. Essentially, he asked the student to solve computer vision over the course of a summer. This was like an internship project. And here we are 50 years later, still solving computer vision. So yeah, it's that hard. And it is also said that Gerald Sussman, who was the undergraduate who was given this task, never actually worked on computer vision again. All right, so what do? How do we solve this problem? Well, machine learning to the rescue. Machine learning is useful for such scenarios where there exists pattern in your data, but you cannot pin down that pattern. You cannot write down mathematically or programmatically what that pattern is. However, you have a lot of data to learn that pattern from. So in our case, if we want the computer to recognize the images of person, we need to feed it lots and lots of images of person, of different people, and hope that it can figure out the pattern. So compared to this traditional programming paradigm, where you feed the computer the program and the data, and it gives you the output, which is the label person. In machine learning, what you do is the other way around. So you still feed the data, so you're still feeding the images, but instead of feeding the program, you're feeding the output, you're feeding the label person. And the output in this case is the program. So the computer is outputting the program that can identify a person from the image. Isn't that cool? All right. In machine learning, there are usually two phases, training and testing. And those of you who already know, you can imagine I'm talking about mostly supervised learning. So you have these two phases. During training, what happens is you feed a lot of data and the corresponding labels, the corresponding outputs to the computer, and the computer then gives you the program that works for most of your input data. So note that the program may not work for 100% of your training data, because even the computer is not perfect in figuring out a perfect program. And once you have figured out this program, during test time, you feed the program that you just figured out to the computer along with new data. So new images of people that it has not seen before. And you expect the computer to label these images also as person, right? So you want to build a general program that can identify any person, not just a person, right? So in our case, let's say you have learned a program that can recognize people in images. During testing, I can give it images of people it has not seen before, and it should be able to classify those new images as person images. All right, now let's look at how we learned this program during the training phase. So the program that we want to learn can mathematically be described as learning a mapping f from x to y. So in this case, this mapping f is the program that we want to learn. X is the input data, so images in our case, and y is the output label. In our running example, this is person label. Right, so label can be like person, sky, water, and so on. You can also think of this in a different scenario. For example, you have emails and you want to classify spam versus not spam. So our email clients already do this, right? So for an incoming email, they sort of automatically classify that maybe this is spam email, this is not. So in this case, you are still learning a program, but the input is email in a text format, not in an image format. So it's basically the text of the email, and the output is the category label, so whether it is spam or not, it's a binary label. It is also applicable for machine translation. So you guys must have used Google Translate to, if you want to like translate from one language to the other. So you can map this scenario to the same scenario of like learning a mapping f from x to y, where x in this case is your input text in one language. On this slide, it is German, and y is the other language, English, right? So you want to translate from German to English, x to y, and you are learning a program, the mapping. It is also applicable for speech recognition. So x is your input speech, and y is the speech is a continuous audio signal, and y is the text. So you want to transcribe the audio waveform into text. All right, so machine learning is not just useful for computer vision, but also for natural language processing, where instead of images, we are processing text, for example, email classification. It is also useful for speech processing, where we are processing speech, for robotics, and so on. So machine learning is useful for artificial intelligence in general, where one way to define artificial intelligence is as follows. The science and engineering of making computers behave in ways that until recently we thought required human intelligence, right? So being able to identify objects in your surrounding, being able to read text and understand that is human intelligence. And if we can make a computer do that, which is a pretty difficult task, then we would say that now we have made an AI system. Any questions so far?
Not yet.
All right. So now let's come back to this program, the mapping F that we want to learn. And this will, which will basically let us identify person, sky, water, etc. from an image, right? If we talk about computer vision, typically the process of going from the image to the label. So for example, in this case, you are feeding the computer an image of a car and you expect it to produce this label car. So typically this process looks like the following. And this two blocks, the set of these two blocks is the program that we have been talking so far, that this is the program that you want to build, that given an image can output the label. So as you see here, this program consists of two sub-modules or sub-programs, if you will. The first of these sub-programs is called feature extractor. So let's see, just to give you an idea of what that means. Okay, so let's say you are given this image of a person, and obviously you want your program to identify this image as that of a person, right? Clearly, there is too much information in this image. There are too many pixels. So remember that matrix consisting of numbers is just a big matrix consisting of too many numbers. It's very difficult for the computer to identify any patterns. Okay, so is there a way to reduce the amount of information in this image? Can we provide a reduced information image to the computer so that maybe it has easier time identifying the pattern? For instance, what if you apply a filter to the given image so that the resulting image looks like this? Now, how is this resulting image different from the original one? Well, in this image, only the contours are highlighted and rest of the information is suppressed. So basically this new image has less information compared to the original image, but it is more manageable for the computer in terms of identifying patterns. So this is an example of feature extraction. Basically, the specific features we are extracting are the contours, and the resulting image can be called as a filtered image, or it can be called as a feature. Similarly, in computer vision, what we do is, given an image, we extract multiple such images. Some of these highlight the contours, some of these highlight the texture, and so on. So we build like multiple feature maps, and then we feed that to the next subprogram. All right, so we got our features, and then we pass those features through this next subprogram, which we call classifier. So basically this classifier classifies those feature images into the label car. Does that make sense? All right. So until few years ago in the field of computer vision, the programs for extracting the features were actually not learned. So they were not learned using machine learning. They were actually hand designed. So what do I mean by hand design? Someone would sit down and write that program to extract all these features. And only the classifier part was learned using machine learning. So this was the typical pipeline in computer vision until few years ago. And you can see that this sort of pipeline generalizes to other fields as well. So even in speech processing, where the input is speech waveform, you had a similar pipeline. You extract some features and then you feed it to a classifier that is, in this case, the output are the phonemes corresponding to this waveform. And even in natural language processing, I feed my input, which is a text sentence. This burrito place is yummy and fun. I extract some features, feed it to a classifier, and do my task. In this case, the task is predicting whether this sentence has positive sentiment or negative sentiment, right? So if you talk about yummy and fun, it's positive sentiment, and hence the output is positive. And in all of these cases, only this classifier was learned using machine learning. This part was actually hand coded. Then what happened with the advent of deep learning in 2012, you might have heard this phrase, deep learning. Now, even this part of extracting the features is learned using machine learning. It's no longer hand designed. Why? Because it gives you much better performance when you learn this using machine learning. Because there are so many different types of programs you can write. And as humans, we are not capable of writing all those kinds of programs, but a computer has much faster and easier time figuring out those programs. And this paradigm in the deep learning era is called end-to-end. Basically, what that means is everything is trained using end-to-end design. Everything in the pipeline is learned using machine learning. There is no hand designing of features. All right, so that marks the end of the basics of computer vision and machine learning. There is so much to this, and I was just able to provide like a bird's eye view of the basics so that it can give you, it can set the ground for what's going to come next. So any questions?
So if you have any questions, please type in the chat box, or you could directly ask. Unmute your mic and you can ask. I think we don't have any questions so far. I think Aishwarya, you can continue.
All right. So next I want to talk about little bit about my research during my PhD, and I'm also continuing to pursue the same line of research at DeepMind. So I'm going to talk about my research on this topic of visual question answering, also known as VQA. So, so far we have been looking at this task where you are given an image and you want to predict label, right? That it is person, sky, water, and so on. So there used to be one input and one output or multiple outputs. In this case, in the VQA task, there are actually two inputs. So there is this image and there is also a question written in text form. So for example, for this image, the question is, what is the mustache made of? And these two inputs are fed to your computer, or we can call it AI system, and we expect it to output the answer to this question by looking at the image, right? So if I show you this image and I ask you the question, what is the mustache made of? You would probably say bananas, right? So this is the task. This is what we want the system to do. And just to give you a better flavor of what this task is, let me actually show you a demo of a system which is working. So you can ask it questions and it can tell you the answers. So this demo is hosted on this page called CloudCV. You guys can all access it. It is on this website, vqa.cloudcv.org. The idea here is that you can, you can upload any image. So let me try and upload this image. Oops. And then you can go ahead and ask questions. So I'll show you some questions and then I'm going to ask you to ask questions. So be ready. So let's say, let me ask, can you guys see it at enough resolution?
Yeah, we can.
Okay. What is in the picture, right? The question is for this image. And the model is going to show me the responses. So it's going to show like 5 different responses, but we are only going to look at the first one because that is the most confident response by the model. So the model says, or the AI system or the computer says that what is in the picture? Girl. That makes sense, right? I can ask, what is the girl doing? And it says eating, which makes sense. She is about to eat the donut. I can ask, what is the girl eating? Right? It says donut, which is correct. I can ask what color is the girl's shirt. It says pink, which makes sense. I can also ask how many girls are there. And it says 2 because you can see there's another girl sitting at the table here. So you can ask it all different kinds of questions as long as the question is about this image, and it should be able to give you a response. So what question do you want to ask?
So there is a question, in which room the girl is? I don't know. In which room the girl is?
Dining room.
Dining room. Wow. Awesome. Maybe.
Next question.
Where is the girl?
School. We don't know if it is school or not, but who knows?
How many boys do we see?
Good question. Well, the model knows there is no boy.
Okay. What is the drink in the plastic glass?
Juice. Looks like apple juice to me.
Okay. All right. So there is another question. This is not for probably asking. This is a direct question to you. How is the AI identifying the color of the shirt if the AI is coded to form contour lines?
Oh, so the contour line example that I gave was actually just one of the various features that you extract from the image. So contour line is basically, the idea is to see like patterns, right? So maybe if I extract contour line, it can say that the picture is of that of a person, but you extract many more features. So for example, in order to answer this question about color, you actually extract features about color. So image is a colored image, right? So RGB values. So there are different other features that encode this information about color. So you extract like a whole set of features to be able to ask any question about color or pattern, like shapes and so on.
So there are a couple of other questions. Maybe I would take last question.
Go ahead, take all of them.
All right. Okay, let's do that. What other girl is doing? What other girl is doing? What the other girl is doing? Yeah.
Eating. Maybe she's more like thinking.
Yeah, actually, she's eating. Yeah, she's putting something in the mind. And what is the age of the girl? What is the age of the girl?
That is a good question.
Inferential question. 6. Good. That's pretty good. What does the girl holds with her left hand?
What is the girl holding with her left hand?
Left hand, nothing. Okay, yeah.
That's incorrect. She's holding the juice glass.
Is the girl wearing pinkish red shirt?
Pinkish red what?
Pinkish red shirt. Pinkish red shirt.
Yes.
Okay. Is the girl smiling?
You got it. So you figured out a loophole in the model. That's good. Maybe we can proceed from here.
So yeah, so that looks pretty, it's very intuitive to see that she is smiling, but the program said no.
Yeah, because the program is not at all perfect. There are many problems which I'm going to talk about next.
How many eyes do I see?
Again, good question.
All right.
You're building the system.
And we have a question for you. How would the AI know that which is the first girl and which is the other girl?
That's a good question. So imagine if there was a human being at the other end, right? Like you were talking to your friend and then you were asking questions about the image. You wouldn't say first girl, second girl, right? Because you don't know what the other human would interpret from that. You would probably say the girl on the right and the girl on the left. Or you would say the girl wearing the pink shirt and the girl wearing the green shirt, right? So you want to have some sort of reference mechanism that the other person will also be able to understand, right? So like basically, when we talk to the system, we sort of imagine that there's a human on the other side, and we're talking to the human. And that is what we are building the system to do, to be able to replicate how humans understand language.
Okay, so there are a couple of more questions. Maybe I'll take the last question. What animals are drawn on her shirt?
Bear, cat, I don't know what, maybe there's a bear, maybe, I don't know.
No, I think it is, I think a dog probably. Anyway, is the girl, okay, the last probably the question, which girl is looking more happier? That's a very interesting question.
Right.
Okay, all right. Okay,
Maybe?
I think we should continue.
All right. I hope you guys enjoyed that. So let's see. So I talked about this task, right? Where you're given an image and a question and you're building a program that can output the answer. But why do we even care about this task? Does it have any application? Yes. So this can be used in various applications. For example, it can be used for visually impaired people, like blind people who want to like navigate in their surroundings. So for example, this person wants to cross the street, but he doesn't know whether he can or not, because he doesn't know whether there are vehicles coming on the road or not. So if he has access to such a system, who he can talk to in language, right? So here we were typing, but you can also imagine speaking. And then if he can talk to such a system, the system can tell him, no, don't cross this street now, right? It can also be, and in fact, folks from CMU built a mobile app called VizViz, which essentially lets blind users take pictures of day-to-day objects and ask questions. So for example, this lady took a picture of this canned container and she asked, can you please tell me what this can is? And then what they do is they send this data, the image and the question, over to cloud workers, basically people, sighted people who can see on the internet, and then they type responses to this question. And that response is then sent back to the lady, and now she can go ahead and do whatever she wanted to do. So our research here is basically trying to automate the job of these cloud workers who are sitting there and typing the response. Another application of VQA is what we call situational impairedness, not visual impairedness. So basically, let's say there is this surveillance camera, which is continuously recording a lot of videos, right? And then something funny happens, some kind of theft, let's say, and then you want to know who, you want to like identify the suspect, right? So one way to do it is, for example, you want to ask the question, what kind of car did the man in that shirt live in? One way to do that would be, as a human, you would browse through like tons of that video data and identify the answer to this question, but that can be very tedious, right, and frustrating. So if you have this automatic system, you can issue this query and it can, in an ideal world, it can give you the answer. And such a visual question answering system can also be used for personal assistant. So if you want to interact with a robot in your house, you can ask questions like, is my laptop in my bedroom upstairs, right? All right, so in 2015, to be able to train this AI systems on for this task, we collected a large scale data set. So what is a data set? Data set basically means large collection of images, questions and answers. And why did we have to do this? Because the model that you just saw, the demo that I was showing, it has been trained on millions of data points. And then after that much training, it is this much capable of answering questions, right? So you need lots and lots of data. So that's what we did. These images come from internet, and these questions that you see here are actually provided by human beings. So there is this platform called Amazon Mechanical Turk, where people like you and me can provide the questions and answers, and we pay them, right? So that's how we collected all this data. So let me walk you through some of the examples here. So in this data set, which we call VQA data set, there are questions about objects, such as what is the mustache made of? There are questions asking about counts of objects, such as how many slices of pizza are there. Question about fine-grained recognition, which basically means that you want to identify the fine-grained categories. So in this case, not just is there a pizza, but is there a vegetarian pizza, right? So what is like the type of pizza? And in this work, we also collected questions that need common sense reasoning. So this was new because, during that time in computer vision, people were not focusing that much on common sense, because even if you forget about common sense, it is a hard problem in itself. So in this case, we have questions like, does this person have 20/20 vision? So what is the common sense aspect here? The common sense aspect is that you need to know what 20/20 vision is, right? So if you're talking to me as a human being who understands English, also understands that 20/20 vision means having perfect vision, which means not wearing glasses. So I will basically translate this question into, is this person wearing glasses or not? And that will be the answer to this question, right? So the machine also needs to know the meaning of this phrase 20/20 vision, and we call that common sense. And I think some of you guys were also asking questions like, what is the age of the kids, right? That is also a commonsensical question, because you need to know more than what you just see in the image. You need to know how old people look like when they are 6 years old, right? All right. So in this data set that we collected, we have more than 250,000 images, more than 3/4 million questions, and about 10 million answers. So this is like a humongous data set. And after collecting all this, so by the way, this was collected like over the course of several months. And after collecting this data set, we released it publicly on this website, which I would encourage you to go out and check. So this is freely available. You can download the data set, you can play with it. All right. In the same work, we also built a preliminary model to be able to solve this task. The demo that I was showing is that...
Aishwarya, there is one question. Shall I read it to you?
Yes, please.
Any insight on few short VQA? Looks like the VQA system requires a lot of data to learn common representation for images and text.
What was the first part? I missed that. Insight.
Any insight on few short VQA?
Yeah, so these systems do require lots of data. There has been ongoing research in few shot. So let me explain to the rest of people what few shot means. So basically, let's say you saw a bunch of images of dogs, right? You know to identify dog from an image, but you have not seen so many images of cat. But you know that there are like common, like shared representations between dog and cat. Dog also has 4 legs, cat also has 4 legs. There are like similar things. So few shot basically means only feeding few images of cat, knowing that the model knows dog, and then being able to classify cat. So in the VQA literature, right now, there has not been a lot of work in few shot, because even without few shot, even if you feed lots of data, it is a hard problem. Does that make sense? Okay.
Okay, so there's another one. Have you used some kind of language models to impart common sense?
Right. So in this slide, I'm going to talk about, I'm going to show you how a typical model looks like. But more recently, people have been using larger and larger language models. So language model basically means, let's say you mine all the text from Wikipedia, right? So you have like large amounts of Wikipedia text, and then you learn a model that can, given one word or given one sentence, can predict the next sentence. So basically the model is trying to learn the structure in the language. So for example, we know certain structure in English, right? Like a singular noun is followed by plural verb. So can we train a model to learn that kind of thing? Is called language modeling. Can you learn common sense using language modeling? To a certain degree, yes, as long as that common sense is written in the web. So for example, we know that birds fly. If it is written somewhere in Wikipedia or internet that birds fly, and if model sees that multiple times, then it learns that common sense that yes, birds do fly. That makes sense?
Yeah, I think, yeah.
Okay. All right. So in this work, we built this preliminary model to be able to do visual question answering. So we have two inputs, right? Image and the question. The question is how many horses are in this image. Then we feed this image through a network, which is a program, right? So imagine this whole network as consisting of multiple sub-networks, so multiple sub-programs, and the output of this thing is a vector. So it's a feature. Basically, you are extracting features, right? So what is the feature in this case? It is a vector. And what is a vector? It is a list of numbers. So this list of numbers consisting of 4096 numbers essentially has information about some important aspects of this image, right? So maybe it has, like, you see, like this is like the contour kind of image that I showed you. This is at the very beginning, but then you run more programs on top of these, and you get a much high level feature. So for example, this feature will have information like there is a horse, there is again a horse, and there are two people, right? So it is kind of a simplified representation of this image. And then, so that we obtained from running this program, but our job is to get to the answer, right? But to be able to do that, we have the question, how many horses are in this image? And this is one of the language model. So basically this is another kind of model, another program that gives us another vector. Now that vector is about this question. So that vector is again like a feature. And that has information like maybe the question is asking about horse, right? So now we have these two vectors, and then comes our classifier. So we combine these two vectors, we feed it through a classification network or a classifier, and that gives us the output, which is 2, right? The question is how many horses are in this image? The answer will be 2. So this is like a typical visual question answering system. And this was what we built in 2015. And we are like 5 years from then, there has been a lot of changes, a lot of improvement in this kind of network. Any questions here?
Not, I don't have any questions here.
Okay.
Yeah, go on.
Right. So as I said, that network that we built was in 2015. And then what we do is every year, we organize competition. And the competition is basically for people to, predict the responses to certain questions and answers. So we have like a test data set, which has some questions and images, and people have to predict, build systems, write programs that can generate the answers. And then we have like a leaderboard, and we rank people on whose performance was the best. So we have been doing this like for 5 years now. There should be like another point here for 2020. And over the course of 5 years, the performance has improved by 20%. So when we started in 2015, the network that I just showed you, that performance was 55%. So what 55% means is that, let's say if you have 100 image question pairs, then only 55 of them, the model is getting right. as in the answer is correct. But for the rest, the answer is not. But today, it's around 76%, right? So that's a huge improvement. And when we test these models, it's not on 100 image question pairs. It's on like tens of thousands image question pairs.
I have a few questions here.
Yeah.
So I'll read all three of them, and then you can choose in which order you would like to answer. Can you explain classification again, please? That's one question. That is from Abhinav. And Rishabh is asking how to fuse language and image features. Is it direct contact? Is it direct concat or averaging of features? Rishiraj is asking, yes, can you please explain the fusion of language and image features again?
Sounds good. So the last two questions are similar. Classification, right? So essentially classification is you have one image and then you feed it through this network which computes the program and gives you the label for that image. So if I give you an image of a dog, it should tell me that there is a dog. If I give you an image of a cat, it should tell me that it has a cat, right? And that program consists of two steps. First, you extract features, like an example that I gave you, and then you feed that feature through a classifier. This classifier and feature in the deep learning era, it's like one thing. There is no separation right now in deep learning era. So it's like one gigantic network that you learn using machine learning that can go from dog, image of the dog to a dog. So that is classification. Coming back to the second and the third question about fusion. So fusion basically, what they're asking is you have like a feature for the image, you have a feature for the language. How do you combine? How do you fuse those two, right? It is actually a well-studied problem in itself because in some sense you want to combine the similar. So let's say you have like a 10-dimension vector for image, 10-dimension vector for the language, and let's say each dimension corresponds to one item, right? So if the question is asking about horse, and then think that there is one dimension in this vector that is about horse. And in the image, there is one dimension that is about horse, the other dimension is about person, and so on. So you want to match the same dimension, right? So you want to match the entry from corresponding to the horse from the language and the entry corresponding to the horse from the image side with each other. But it's not like, we still don't know what is the best way to do it. So what people typically do is they take these two vectors and they either multiply pointwise, which basically means that multiply the corresponding entries. So like 10 dimension, multiply each entry, or you can concatenate, which basically stack these two on top. So you get a 20-dimension vector. Sometimes you even average. So there are a bunch of different ways to do it. There is no sort of set in stone rule that you should do it this way. It depends on what gives you better performance. All right?
Yeah, go on.
So we have 7 minutes, right?
Yeah, you can take, a couple of extra minutes. Okay.
Sounds good.
Yeah.
Right. So we saw that there has been a lot of improvement, right? This chart that I just showed you, the 20% improvement is really a big deal. But even after that, the models that we have, they are not that great. And in the demo that I showed, some of you were actually able to ask questions, right? Where you saw that the answer is not right. I think the question was, is the girl smiling? How many eyes are there? And it said 2 instead of 4. So I was actually going to show the demo again to give you like examples of questions where it fails, but I think I'm going to skip this in the interest of time. We already saw some of that. So in 2016, what we did was we wanted to analyze systematically where do these models fail. So I'll show you some of the examples of the analysis we did. Hopefully that will give you a sense for are there patterns in the kind of things that these models fail at. So for example, if you ask model this question, what color are the safety cones for this image, you can see that there are green cones here, right? But the model predicts orange as the answer. And we were curious to know why it is predicting orange instead of green. So then what we did was we looked at the examples from the training data, which are similar to this question, which the model has seen. So training data basically means the model knows the answers to those questions, right? So for example, this is what it has seen. What color are the cones? The answer is orange. What color is the cone? The answer is orange again. What color are the cones? The answer is orange again. So what we found was that in the training data, the model has mostly seen questions about orange cones, right? And that is why it is failing during testing, because during testing, I'm asking it questions about green cones, but it is so good at identifying orange cones, but not so good at identifying green cones. Excuse me. So basically what is going on here is that when the model is learning from these kind of data points, it is sort of memorizing that, okay, if you ask me a question about the cone, I will just say orange. Why? Because most of the cones are orange in nature, right? But that's bad. Why it is bad? Because if I ask it a question about green cone, then it is failing, right? It still says orange. So that is one kind of problem. And note that this is not a problem for human beings, right? Even if you have mostly seen orange cones, you will still be able to correctly identify the color of this cone. Because you know green, right? Like you have seen green for other objects. Green plate, green whatever. This is another example. So if we ask this question to the model, are they playing a game? It says yes. But if we just ask, are they, like I don't even finish the question, it still says yes. That is very, very non-human like, right? Like if I ask you this question, are they, you will be like, what is the question? Like this is an incomplete question. But to the model, it doesn't matter. It still says yes. So again, there is kind of memorization or bias that this model is learning, that whenever the question starts with the words are they, I will say yes, because mostly that is right. Here is another example. The question is how many zebras for this image. And for this, the model correctly predicts the answer 2. But it says 2 even for this image, right? Which is incorrect because there is only one zebra. It says 2 for this image as well and says 2 for this image. So basically it is not looking at the image, right? It seems like whenever I ask how many zebras, it just says 2 without looking at the image, which is bad. It should be looking at the image, because if you ask me the question, I will look at the image and then I will produce the response. But it seems like for the model, it is too difficult to learn from image and just like produce the answer based on the question. You might wonder, like, why is this bad, right? Why do we care about such behavior? And when I say such behavior, I'm basically saying biased systems. So it's bad because, it can lead to bad consequences. So you guys might have seen this news article where Google Photos labeled African Americans as gorillas. So this is really, really bad, right? So that is the kind of thing that we don't want in our VQA system, because if we deploy it for practical purposes, if it is biased, then it can lead to severe consequences. So what can we do to tackle these problems? So for those people who are interested in knowing more, I'm going to list some of the works we did to tackle these issues. I unfortunately don't have time to go into the details, but if you are interested, you can read the papers online. So one of the things we did was we changed the evaluation protocol. We built a new kind of model design that is less biased. And we also built like a new way of training the model, new objective function. All right, so far I talked about the progress we have made in visual question answering. And I talked about one challenge. So all of these examples that I was showing is actually referring to this challenge of visual grounding. So what do we mean by visual grounding? So here there are 2 inputs to the model, right? The question and the image. So what is happening is that the model is sort of ignoring the image and producing the answer based on the question. So we say that it is not grounded in the visual domain. It is not visually grounded, which is a problem. There has been a lot of work in this space to improve the performance of the models, but still long way to go. There is this other issue of counting, that most of these models are not good at counting questions. So for example, how many men are sitting at the table? It needs to identify that, okay, the question is about men who are sitting at the table, and then like identify the regions of the image where there are men, sum those counts, and then output. The models we have right now are not sophisticated yet to be able to answer these types of questions. Similarly, questions where you need to read from the image, right? So the question is, what does the red sign say? You need to read this text, reduce speed, and then produce that as an answer. Our models are not yet good at that kind of thing. The knowledge-based reasoning that I talked about, they don't yet know what 20/20 vision means because they don't have common sense. And there are many more challenges. I'm not going to be able to talk about that. But basically, the bottom line is that there has been a lot of progress over the past few years, but there are still quite a few interesting challenges that keep you busy in doing research, right? All right. So before I close, the last thing I want to talk about is the secret sauce of my journey with AI so far. And that secret sauce is the support system that I had during my PhD and even now, which made it possible to do what I did. So first of all, my advisors, Dhruv, Batra, and Devi, Parikh, I told you that when I started my graduate program, I didn't know much about machine learning, computer vision, or AI. Dhruv and Devi became my mentors and provided constant guidance, support, and encouragement. They not only shaped my research and career, but my thinking as well. So I think I was really lucky to have such wonderful advisors. And thanks again to Professor Raman for pointing me in the right direction. Another great thing that happened with me was my partner, Yash Goyal, who, by the way, I met at IIT Gandhinagar. He also got admitted to Virginia Tech, and that too with the same advisor. So both of us pursued our PhD in the same lab. We then moved to Georgia Tech as well. And he was the biggest source of my emotional and mental strength throughout my PhD. And finally, my parents, Indu Agrawal and Sanjay Agrawal, 6 years ago, it wasn't easy for them to send their only child, and that to a girl child, thousands of miles away to pursue PhD. But they did that. And they always, understood my life choices and let me follow my dreams. So it was great. I didn't have any kind of restrictions. So overall, what I want to say is that I feel like I was lucky to have such a strong support system around me, and that really helped me do my PhD smoothly and generally be excited about research. So that's great. All right, so that's all I have. Thanks a lot for listening.